Hello, everyone. If you're here in the right place, we're talking about Amazon ECR, and we're going to do a deep dive on image optimization. Now, just to get started, what to expect in this session. So we're going to go over sort of how Docker images are built, so you can really understand and make better educated decisions on optimizing your own image builds. I'm going to assume a fair amount of familiarity, since it's a 400-level talk, with Docker and ECR and ECS. I'm going to have a lot of content in my slides here. I'm going to make sure that I go through so you can see a little bit, but these slides are also going to be available afterwards, so you can sort of step through all the commands and follow through again. So really, the goal is to sort of educate you here and see how Docker images are built, composed, and how the registry API works. We're also going to talk a little bit about CI/CD best practices, and then Mal's going to come up here and talk a little bit about ECR learnings and best practices that they have at Pinterest. So a little bit about me. I work for AWS in the EC2 Container Registry. I've been at Amazon for over 10 years, and I've worked on a lot of different teams. I worked on the retail marketplace team, Amazon Local, Amazon Restaurants, and then I've been with EC2 for about 2 years now. I really like sort of understanding how things work, taking them apart, putting them back together. And so I'm also really passionate about containers and sort of what they allow for developers and what they allow you to do. And I've worked on the container registry since it launched, so I have a pretty good understanding and low-level understanding of how it actually all fits together. Now, if you're not familiar, Amazon EC2 Container Registry is a fully managed, highly available, and secure Docker-compatible container registry. It allows you to sort of drop in with your existing Docker commands. If you're doing Docker pushes and pulls, it all implements the API, so you don't have to worry about it. But it's also available. We're in 9 different regions today, and also integrates with things like IAM and resource policies, so that way you can secure and really lock things down. We also provide CloudTrail integration and a number of the others. So it really is a Docker registry that's designed to work best with AWS. Now, a lot of the tips that I'm going to give today, while they're true for most registries and most container images, these will also hold true for ECR. So we'll talk a little bit about how Docker images are constructed and how they work. So first up, Docker images themselves are packaged application code, binaries, and they really basically provide you a portable way of having your build software go to production. So one of the common problems that a lot of customers have had before and software developers have had for a long time is making sure that that reproducible build that you had on your desktop works in production. Even down to sort of complex build systems that have had before in the past, even things like LD library paths and shared dependencies can cause a lot of problems. And even down in sort of a lot of modern teams, we end up having multiple languages implemented on the same host, multiple dependent libraries, different SSL versions, even down to glibc. Now, Docker allows you to build portable images that can actually go from a base host to base host without having to worry about those. You know exactly what happened in development, and what you had is exactly what you have in production. So Docker images themselves are actually comprised of layers. Layers are immutable. They're read-only. They actually hold both file data and configuration data for each part that makes up an image. In this case, this is a Hello reInvent example. It's tagged latest, and you can see that it has 3 layers. Now, each layer, because of Docker's union file system, will override the contents of the previous at runtime. So if you have a file in the top layer, the next layer below it, if it has the same file, it'll override that file and use it instead. This is sort of what allows you to sort of build and compose those to create that image. Now, a running container is a Docker image that's being executed that has a container layer that's read-write. This actually holds the container data at runtime, and then when it exits, you can either save that intermediate layer or have it cleaned up. Now, and this is actually how Docker images themselves are built inside Docker. So you run a blank image. You go ahead and you execute some code. It saves that read-write file system with a content addressable hash, and then it adds it to the layer. So we can see later as we go through some build examples, when you're actually building, you're just using containers. But using this directly would be kind of cumbersome. So the Docker file syntax is what really allows you to sort of express your image in a nice, clean format. You can see that more or less, a lot of the lines in a Docker file can usually correspond to a layer, one or more layers. So in this case, we have an Alpine layer, which is a base layer. This is a Linux base image that we're starting from. It only has a single layer, so it's one, but you could think that if this points to, say, an Ubuntu image or a language-specific version like Java or Ruby, that actually might have multiple layers. I have a maintainer line here and a command line as well. So looking at that a little closer, again, we have a from build that we have. We have a maintainer line, which just is putting metadata about who owns and runs this and manages this image for other developers to see. And then we have an actual command. In this case, it's just echoing hello reinvent. Now, when we actually run our Docker build command, we can sort of look at that output and see what's happening. We can see that it's running from Alpine. It's adding the extra maintainer. It's removing the intermediate container after it runs. It's setting up the command for hello reinvent and running it again. Now, each of those cases, it's running those intermediate containers and then cleaning up afterwards. And that's sort of important. Those temporary read-write layers are then removed, and you have basically your image built that you can push anywhere you want. Now, we can actually use the Docker history command to inspect that image. So you can see this actually goes from top to bottom. It's actually set, it's backwards from what the order it's been built. But you can see the bottom layer actually has the add file, and that's a 4 meg layer. That is a very, Alpine is a very lightweight, small Linux distribution as a base. And then we have the maintainer line and then the command line. Now you'll notice that while the base layer is 4 megs, the sizes for each of the other config layers are actually 0 bytes. Since there isn't any file system data that needs to be required for those, they're just configuration. It actually isn't preserved along with it. So they end up being empty, what we call empty layers. We'll see a little bit more about that later. So we can also look at our history for Alpine, and we can see it's actually the same as the top layer that we had before. It's the same immutable thing. So if I can have something that's based off of an existing image, that's actually the exact same history. So if I base all of my images off of, say, Alpine, I know that that common layer can be used across different images on my host when I pull in production. So coming up with a common base layer that you're using for all of your container instances, if they follow a similar pattern or stack, can actually help make a lot of portability in production. But it may depend on your varying workloads, because you may have different teams that have different dependencies and needs and rely on different distributions. Now, if we want to make a code change, we can go ahead and we've made a change to our Docker file. In this case, we're just adding some hearts to our echo command, and we're going to rebuild. Now, we'll notice in this particular case, it was actually able to use the build cache. So here, we can see that rather than running the intermediate container, saving the state and exiting, it's actually going to use that cache layer. So Docker, in this case, noticed that the maintainer line hadn't been changed, so it was able to not have to execute that command, initialize another container. Really sort of understanding and optimizing how build caches are used are really going to help you in your build and CI/CD systems. In this particular case, our command did change, so it knows that that's invalidated and has to rerun that build layer. And it runs it there. So now that we have a kind of a basic understanding of images, we can talk about how we can actually improve on some image builds. We're going to go through a couple examples here just to get started. So first, this is a simple Ruby application. We're picking Ruby 2.3. It has some gem file dependencies. We're going to go ahead and bundle those up and then add our application code. Now, the first thing we notice is that we're setting Ruby 2.3. You really want to sort of isolate down a specific base package version, because if you just say Ruby latest, it could be that one developer is running a build on one desktop, another developer is running it in the CI system. It ends up grabbing a different version of Ruby. So I would even recommend going further than this and actually pinpointing down to a specific patch version or minor version just to keep consistency. The next thing is we're adding our gem file and our gem file lock. And in a Ruby application, all of your dependencies are sort of defined ahead of time. So your gem file, while it has the high-level dependencies, the gem file lock has all of your fully resolved downstream dependencies. So that way, if I build my image, regardless of where I'm building it, I'm getting the exact same gems installed. I'm adding my source code after that, and then I'm running my simple hello. Looking at our gem file, we just have a colorized gem. So we're just using a simple gem here. The gem file lock will actually, at sort of build time and checking into your source code, will actually have the very specific version of colorize. Looking at our source code, we're just going to sort of say hello world, but we're going to give it a little more flair this time. We're going to give it some colors. And we're using the colorized gem to give us some fun ASCII. Now, going through our build step in our container, we can see that it's actually adding our gem file lock. It's doing our bundle install, and it's doing that bundle install on the container instead of on my host. It's actually going to go down to Ruby gems, download my gems, and build those into the build cache. So we can see in the user local bundle is actually where it's stored inside that container image. And then later it adds my application code. We can see that, again, it's going to remove the intermediate containers as it's being built. There's the add for our source code. And if we actually run it, we can see we finally get some nice colorized output. And let's say we want to make a code change in this particular case. We want to add some more hearts, again, to our ASCII output. And so we've made that code change down there at the bottom. But we haven't changed any of our gem dependencies. None of our build dependencies have really changed. We rerun our build, and we can see in this case, it's actually able to cache the gem file lock and the bundle install, which means I didn't have to re-download gems from my build instance. Now, this is a tip really here of just separating those build time from your actual build based on your actual application code. Most teams end up having a lot more changes to their application code than they do on their build dependencies. So being able to really sort of separate these will allow you to sort of optimize on those build caches. And because our code has actually changed, in this particular case, it's going to have to rerun. But it only has to rerun on that last layer. We run our hello reinvent again. This time we get our hearts in nice color. And so the takeaways here that I really want you to go away with is sticking to specific versions of base layers allow to give stability from developer to developer and give you consistent builds. It also means that at deployment time, if you sort of opt into those new versions of, say, your base layer, like Ruby, for example, you know that if you're moving from, say, 2.3 to 2.4 to 3.0, you know when that's going to happen, and that means only those new base layers are going to be deployed at that particular point in time. Most deployments are going to be fairly small because they're just adding your Ruby code that's changed. So separating your application code from its dependencies really helps you sort of optimize what you're actually building and deploying. So next up, we're going to walk through a bit of a Go example. In this particular case, again, I'm going to try to pick a specific version. We're using Go 1.7, but you could get more specific down there to a minor version. We're going to actually add our source code and run our Go build inside of our container. Or actually, Go code is just going to say hello world. Again, not something super crazy exciting, but I'm sure your applications are going to be a little bit more advanced. And in this case, we're actually going to go ahead and building our container. Now, when we run our actual application, we get our hello, so we know it works. And let's look at our actual images output. So this is kind of surprising. Go is a compiled language, and so you should have a really small binary at the end of this. But we actually end up having a 674 megabyte layer or image. And that's kind of surprising because it seems that we'd be able to have a binary much smaller than that. And this seems like a lot to sort of build and push all the way out to production. So we can go back to our history command and actually inspect and see sort of what happened here. And in this particular case, we're going to run our history command and going to see all these layers that are coming from. So this all comes from the Go 1.7 base layer. And so all of the things that are above, and again, these go some sort of top to bottom, are everything that you sort of brought in as a part of the Go 1.7. And we can see we first have these apt-get updates and apt-get installs. And that's actually getting all of the build essentials that are required for Go itself to be compiled. Then we actually have all of the Go source code downloaded, which is another 200 megs. And then we finally have our binary after all of those builds. So our binary itself is less than 2 megs, but we have all of these other things that are required for that particular container. So this is sort of the next sort of tip that I'd like to sort of provide you is really sort of understanding that at runtime, you don't necessarily need everything that you need at build time. And while build isolation is great, you really need to sort of figure out a way of isolating these two. And the way that I would recommend, and the way that we've used at ECS as well, is actually isolating build versus runtime containers. Our agent itself builds in this format, so which is fully open source, and you can check it out as well. So looking at our, this is going to be our build container. Looks similar from before, except for we have a volume mount. And we then copy our binary instead of actually running it. So we're using a volume mount to then sort of copy what we need our artifacts out. You can imagine if this was another application, you could do the same, whatever kind of resources, even if it was, say, compressed gzipped JavaScript or whatever resources or artifacts that your application needs at production time. So our build container, or our runtime container here, is actually pretty small. It has from scratch, which is actually an empty base image that has nothing in it, and we're adding our binary, and then we're just running it. So it only contains that our binary needs at runtime. It's a static build, that's it. So we're going to rerun our build, which looks like we had before. It actually builds in our build time container. And we'll notice the differences here is we're adding a volume. And the actual command to copy is to copy the actual binary out of the image. So now we can actually copy that artifact out by doing a Docker run. So we're doing a volume out locally. We're running the container. And all we're really doing is saying, oh, let's take this binary from inside this container and copy it out. And then lastly, now we're running our runtime container. We're actually going to go ahead and just add that binary. Now, the great thing as well here is we're still getting that build level of isolation, which means I could actually be on a host that doesn't even have Go installed. I can run a nice sanitized build, and then I can add all of my artifacts to a separate container that's pushed at runtime. So we know it still works. We rerun our command. We get our hello reinvent. But now, we're only down to less than 2 megs in our layer. And we have 2 layers, and we only have 2 megs for our actual binary application. So now, instead of every single deploy having to deploy that entire stack, I've got a much, much smaller binary. That's really going to make things a lot better at both your CI system having to push all the way up to your registry, as well as download from the registry as well at deployment time. So we've got that, again, 2 megs there. So the overall tips here is just trying to figure out what you actually need at runtime versus what you need at build time. Again, Docker provides a great level of build isolation, so you can ensure that you've got that portable images, and they're very much isolated from those dependencies. But separating out that from your build and runtime container is actually going to improve your pull and push times. And there are applications where, like, this is a static example where you have a binary, which could work well for any sort of statically compiled language. But dynamic languages work for this as well. If you have a Rails stack, for example, you might want to package up all your JavaScript or image assets or your CSS assets. You don't necessarily need that compression to be that sort of JavaScript engine to come with you at runtime. You could actually separate it out at build time and then just package those up for serving later. So these are some of the advanced tips that I don't unfortunately have enough time to cover today. But I'll leave with you as sort of a bit of a homework assignment. So the first thing is you can build your own base images. It's actually quite easy. Base images are what we saw before. We're sort of using Alpine. We used Go. Now, you could have a normal Docker image that gets built, but you could also sort of create your own base layer by creating a local tarball and then importing it. This can be really good if you want to set a common base layer for your entire company. If you have, say, a base distribution with common packages that everyone is going to use, you're kind of trying to unify that stack across things. And that'll mean that if you know that base layer is pushed across all of your build fleet, it's going to make things much better. And on top of that, in Docker 1.13, now this is in the RC, so it will, when Docker 1.13 goes finalized, there's actually a squash layer. There's a squash command now. So that allows you to sort of take multiple of those sort of smaller layers and squash them down into a single layer to reduce overhead of having to do lots of smaller pulls. Now, you'll have to be careful with this because you could end up invalidating those other layers. There are cases in which if you're then taking all of your base layers for your base image and adding your application code, you're squashing it to a single one. Now you're pulling the entire image every single time. So you can't really take advantage of that layer level caching on your deployment hosts. So now that we have an idea of how we can sort of build and optimize our images, we'll talk a little bit how the Docker Registry V2 API works. Again, ECR understands and responds and works with this this API. So if we understand how this API actually works between the Docker engine and our registry, we can actually then look at how optimizing our layers and images can actually improve. So the first thing is pulling an image. When we do a Docker pull, you provide a registry URI. In this particular case, for ECR, you're going to use your specific registry URL. And because you can provide this URL with others, it's unique to your account. You provide your image name and your tag. Now, so the Docker daemon, when you tell this, the command's going to hit the daemon, and the daemon's going to say, well, first we need to fetch this image at this particular tag, and for each layer I don't happen to have on the host, I need to go ahead and download it. So translating that to HTTP calls, it does an HTTP GET for /v2 image name manifest tag, and then for each layer that it doesn't have locally, it's a get v2 image name blobs digest. So this is really important. So if I already have a layer on my host, I don't actually have to download it. If I've already cached that sort of base, if I'm using Alpine, if I've already cached that base Alpine image on every single one of my hosts in my ECS fleet, I don't actually have to download that base layer anymore, and I'm just deploying the latest bit of my application code. And really kind of like tuning in those will sort of really help your deployments go much, much faster. Oh, and as a quick note on Docker 110 and above, it actually pulls these layers in parallel. So that's something to sort of look out as well, sort of upgrading at least to that version will give you an idea, so that means it can pull those layers concurrently. You'll still be stuck for the longest layer, so if you have, for some reason, you have one very, very large layer, you're still going to wait on that last layer to pull before it can actually start running. But again, being able to pull lots of small layers concurrently helps quite a bit. Now, pushing an image is exactly the opposite. We're going to do a Docker push, registry URL that you have locally, image name and tag. But the Docker daemon has to do a little bit more work here. For each layer, it has to see, does that layer exist already on the registry? And if it doesn't, then it needs to initiate a layer upload, send the actual data, and then set that it's complete. And when all of those layers are done, it needs to sort of push the manifest saying that the layers are complete. Translating this to the API perspective, we can see it's just doing a head check. It's doing a post to initialize the upload. It's doing a patch to actually send that binary contents for the layer. And then it's doing a put to finalize each individual layer. Now again, from Docker 110 and above, it can actually parallelize these uploads and kind of speed things up. So now we have an image that's actually been pushed. We're going to actually, or no, we have an image that we understand how the APIs work. We're going to actually go through a whole push scenario with sort of ECR here and see how it works. Now we're going to we need to sort of get a temporary set of credentials that we can use to work with ECR. We're going to go ahead and get an authorization token. And then we can actually get that out of the result data here, as well as getting the endpoint that we want to talk to. I'm going to use a little bit of JQ here to do some of the JavaScript parsing. Now I want to fetch out my username and password. That token that we had before was actually just a base64 encoded username and temporary password. This comes back in an HTTP digest format, which is normally sent back and forth. But for our purposes, we want to separate that because we're doing a Docker login. We use a Docker login. We provide that username and password to our ECR URL that we saved before. And because this is probably a little bit more cumbersome to do on a regular basis, this is actually what the ECR's get login command does under the scenes. So you can actually go to the CLI open source and see it pretty much does the same thing, except for it's written in Python instead of Bash. Base64-D, this is what it is on your Mac. So if you're running on Linux, I think it's a lowercase d. So now we're going to go ahead and create a repository here on ECR. So we're going to go ahead and create our hello. We're going to go back to our original example that we had before that we had built. And we're going to save off that image URI so we know exactly what URI to sort of provide when we're actually going to tag our image. And once you're done this exercise, I'd say you can go back and delete that repository. We provide a force command. This is just so if you're deleting a repository and you have images that you haven't deleted, we sort of don't let you unless you pass the force. It's really just sort of a safety mechanism to make things a little bit easier. Now pushing an image, we're going to go ahead and tag that hello back to our image URI and just do a push. Now that we have that image pushed, we can see, well, what does that manifest actually look like? So we can actually do a curl here with that username and password. It's going to set the HTTP digest on the request. Go back to our URL. We're going to go back to that manifest latest. So that's hello is the image name and latest is the tag. And we're going to save that back out to a JSON file so we can use it later. We can start to see the beginning of this JSON file, and that's all an image really is. It's just a JSON file with data. It's going to store in this particular case, it's showing it schema 1. Currently, ECR supports manifest schema 1. We're going to be supporting schema 2 very shortly. You can see that this has our image name and our tag inside of it, as well as the architecture. Next through the file, you can actually see the blob sums. So those are actually refer back to those tars that we saw before, those blobs. And you'll actually notice that the top two actually have the same number. This A3ED95CAE is actually an empty layer. So there's no actual content. It's just an empty tar GZ. And the last one itself is our Alpine layer. So that was our config and run command that we saw before. This is sort of how you could see what they are. Now, in newer versions of Docker, again, the schema 2, it actually removes these config layers and changes the configuration to a separate layer itself that holds all of that data. But schema 1 is still preserved here. Now, this is definitely hard to read, but looking at the history, we can see this V1 compatibility. So now we're actually going to see the Docker container config for every single layer. Now, this is JSON inside of JSON, but you can usually parse this out if you kind of want to see what's going on or if you squint really, really hard. But this is our last layer that actually did our echo hello world. And also because it's the final layer, it has all the runtime configuration that your container needs. So it sets your environment variables, your path, whether or not you have a TTY. This is all your runtime configuration, just sort of stored in the image. And you'll also notice that it has, if you can see it from here, we can probably see it in the next slide a little bit better. There we go. So these are the other two layers. The maintainer line is the first one we see on the top there. It's a little easier to understand, slightly. You can see that it has this container config line. See that command maintainer line there where it has my name? So that's actually how the Docker history command can actually look back at that manifest and see how each layer was built. So you actually go back to a manifest and say, like, well, where did this come from? And in this particular case, all it does is add a config line that says my author is my name. And it's a throwaway layer because it's just a config-based layer. The last layer we can see here doesn't have any configuration other than showing the container config on how it was built. And that's because our Alpine layer is just the actual Alpine binary that we need to actually run our base image. Now lastly, we have a signature here. In Schema 1, signatures can be added inside of the manifest file. This means that the signed manifest as a part of there is all in here. In later versions of Docker, that signature is actually brought outside the manifest, which is a little bit nicer, and it's moved into Notary. So now that we have our manifest file saved, let's go ahead and download the layers. We're going to use a little bit more JQ, which is pretty much my helper for most things. I'm going to pipe that out to a file, and then we're going to do some curl with some xargs. And we're going to download each one of those layers. If you give a -p and a number command too, you can parallelize download, pro xargs tip for anyone. But the -l here is also important because that's actually allowing us to follow redirects. So from ECR, we actually provide pre-signed URLs down to Docker so it can download your images directly from S3. This ensures that you get the best performance because at this point, you're going directly to S3 to actually download everything. And we're saving those blobs out to disk. And again, we're providing our credentials the way we did before. Now looking at our layers, we only actually have 2 that downloaded because two are the same or that empty layer. And we have our 2.2 megs because these are actually gzipped as well. And we can actually just look at them. Man, if you want to, you can just untar them. There's not a lot of magic here. This is just Unix. So you can actually see that I'm not going to show you the entire contents of Alpine. That might be a little boring. But we can see that we have the BusyBox binary, and we have a bunch of symlinks. That's just because it's a small distro. So I've used this trick quite a bit when I look at a layer, and it's way bigger than what I expected. So I'll download it. I'll extract it. I'll see actually what's inside and say, oh, I didn't actually realize that simple command was adding so much to my actual runtime layer. And our empty layer is, in fact, an empty layer. There's nothing in it. It's just a little 4 kilobyte empty tar GZ. Again, at least with the newer versions, this isn't actually sort of transferred. But usually on your host, this is cached pretty quickly. It's only pulled down once. So it can get that empty layer. So the takeaways now that we kind of understand how our APIs work is that really reducing your number of layers means this reduces the number of uploads and downloads that you have. And reducing the actual contents reduces that upload-download time. And every single time you minimize those layer changes themselves, we can actually reduce and faster deployments. So you know if that one last small little layer is the only thing you've changed your application, and you're deploying very, very frequently in your CI system, you're going to get much faster deployments if you just spend a little bit of time going through your Docker images and figuring out what's going on in there. So talking of CI/CD, so going through a little bit of the best practices here, we're going to sort of talk about some tips that we've learned from talking to a lot of our customers. The first thing is come up with a good tagging scheme. A lot of customers might use latest or stable or prod. One of the problems with that is it means it's really hard to sort of stage out your changes. So if I'm using stable and I'm using ECS, it may sort of just go ahead and start using that in my task definition. So we really recommend as a part of your build system, creating a logical sort of version for every single build that you make. And ideally, if you can tie it back to your artifacts, then you can sort of trace that all the way through your production system. So you tag it back to your source code or maybe your Jenkins build identifier. You can know where that actual artifact came from. And that means you can actually stagger your deployments. So if you're using ECS, we'd recommend creating a new task definition in your family, updating your service definition, and then allowing that to sort of gradually roll out. And if you're really interested in blue-green deployments, then we'd recommend is creating a second service with a new task definition and using ELB, creating a new ALB, and then using Route 53 to wait over. So the CI/CD tips that we really have here is the build caches that we mentioned before. So not having to rerun the bundle install means that we can actually take advantage of that here. So being able to sort of rerun in the same build hosts means you're actually going to take advantage of what was already on that host before. You don't have to re-download those gems every single time. And of course, reducing your build to image sizes is going to actually, and reduce the number of layers, is going to actually reduce how much you have to transfer back up to ECR. And of course, we are in 9 regions today. So building and pushing in the same region as possible is actually going to make things much, much, much better. That way you don't have to do any sort of cross-region pushes. So next up, we're going to have Mal come up here, and he's going to talk a little bit about ECR and their usage at Pinterest.
Thanks. Thanks, Scott. First, let me make my speaker load larger. Oh, sorry. First of all, a little bit about me. My name is Mao Gan. I'm working for Pinterest as a site reliability engineer. I came from a background of a traditional enterprise software developer in Oracle database and Java EE land for years. Then I became a performance engineer in a SaaS company. 2 years ago, I switched to the SRE role. And I'm excited about cloud and container technologies. I'm focusing on putting things into containers since I joined Pinterest. Today, I'm very happy to have the chance to share you about a few stories and tips and lessons we learned at Pinterest when running container in AWS. For people who hasn't heard Pinterest, we are the catalog of ideas around the world. Users use Pinterest website or apps to share and discover various ideas of their interests, and often get inspired by amazing ideas to do something awesome in their real lives. And recently, we achieved 100 million weekly active users, and half of them are from outside of the United States. So these are very big milestones for us. You can also see we have a tremendous amount of data, like pins, balls of many users. We store all of them in AWS. Yeah, a little bit of history is Pinterest was built on top of AWS since it was built at 2010. Now we grew a lot, of course, and nowadays we are running tens of thousands EC2 instances, and also we have over 100 petabyte data in S3, which cannot even be packed into one slow mobile track. Okay. Yeah. So when I talking about containers, actually I often mean Docker. Yeah, I expect many audience here already know some information about Docker, so I won't elaborate many benefits of Docker here. So I will explain at Pinterest the major reason for us to adapting Docker from the beginning of this year is because we found Docker is a better tool to build, ship, and run services for internal Pinterest services in a much, much more reliable way. That's what advertised by the Docker company, but to be honest, it's true because the experienced Docker build, it's very helpful for developers. I think so far, the Docker image probably is best format for everyone, every developers to build and ship their services and run in anywhere. It's an innovation which disrupted many traditional tools, for example, apt-get or configuration tool like Puppet or other things. Sorry if you are a Puppet lover, but yeah, that's my opinion. Pinterest actually is a heavy user of Puppet for instance profiling and the service configuration. It played a big role in Pinterest's growth till now. However, we also accumulated many issues because we have a big shared Puppet repo for everything, which now becomes kind of clunky and cause many issues from time to time. So Docker, fortunately, addressed the issues very well because it packages the dependencies into images as much as possible. Hence, it minimized the risk of provisioning and configuration on the host. So first thing when I started to working on Docker in Pinterest is to find a reliable registry solution. We picked ECR because of several reasons. The first one is I don't want to run or maintain our own registry because it takes efforts to run it stable and reliable and keep it upgraded to back where the compatible with the Docker client. So I trust AWS and just like we trust other services in AWS. The second reason is it's fast, it's performant because AWS provided maybe the fastest access path for the ECR. And the third reason is reliable, scalable. As Scott mentioned earlier, the Docker pool actually use URL to directly pull layers from S3. And S3, we are very familiar and we trust it's no doubt reliable and scalable. We did have small issues at the beginning when we used ECR, which is related to the get token request, but we resolved it quickly with AWS kind of support, so it's non-issue anymore. Then there are a few usage I'd like to share with you is firstly, in Pinterest, we have many development instances in EC2. Basically, each developer in Pinterest has a EC2 instances which contains all the dependency, and basically each developer can run a locally Pinterest website on their dev app instances. It was configured by Puppet, but yeah, as I mentioned, Puppet has so many things together, and it's fragile, it's broken all the time. So we did one thing which impacted many developers, which is we put all the developers' dev environment into the Docker image. And so now we have hundreds of dev incidences running Docker engine, and the developer use Docker daily. The second usage is the Jenkins. We have hundreds of also Jenkins slaves to build the Docker image, test Docker image, and also push image, tag image. The third usage is the Mac. Some developer will use Mac, Docker for Mac, and do some testing or development on their laptop. It's totally fun to work with ECR. The fourth one is the Mesos. We have a few Mesos clusters running some Spark streaming jobs together with a few other things. Because Mesos offered the Docker integration to run the container based on Docker image, and we like the Docker image, so we tried the integration. with the ECR, and it works quite well. We can run multiple versions of Spark binary using Docker image pretty well. It's a better way to do the instance configuration. And the last one I'd like to mention is we have also several Dockerized services are running in production. They are in smaller scale, just dozens of nodes, but they work pretty well. We use an in-house deployment tool, which is called Teletron, and it's also open sourced on GitHub. Basically, Teletron allows you to write some shell script to deploy a service, which sounds like a little bit step back from the configuration management tool like Puppet, but actually we found it's a better way to deploy container because the shell script is only service specific. It's not in a shared configuration repo for everything. The isolation it provided is much better for microservices. So we are using the Teletron to configure the host and then use Docker command to run container for these services. Next, this is a sneak peek of our ECR repository and Jenkins job directory we build in-house. Currently, actually, we have over 20 image repo, and we use Jenkins to build and test and tag, then push image into ECR. And we have a policy in-house, which is only Jenkins can push image onto ECR, and the developer should not push image from their laptop or dev instances because they could mess it up. Even you give a git commit ID as a tag for the image, it can still be override by someone if doesn't know where. And we have the GitHub and not GitHub, Git repo, internally Git repo integration with Jenkins. So developer have a commit or pull request can trigger a Jenkins job in a continuous integration way. Yeah, it works pretty well. In Jenkins, we actually just use a plain shell script to invoke the Docker commands to build some image. And also, we have some project use Makefile to manage the image building by invoking the Docker commands. Either way works. And okay, even we have very good experience about Docker, and we think it will help Pinterest in the future. We did hit some Docker issues at Pinterest. The issues are mostly related to the storage driver or the OLIN file systems used by the Docker engine. For example, the AWS one, which is pretty severe. At the early days, we tried Docker. We use the kernel 3.18 at that time. By default, it is AWS storage driver. And it caused the issue, which is container cannot be stopped because it becomes a zombie process on the host. And it's hard to fix, even restart the Docker engine. Then we tried other alternative storage drivers, for example, VFS, which was also not good because it can create huge, it can occupy huge space on the varlib Docker folder when you build a simple image. So it's not it's not efficient to use at all. then we switched to AUF overlay storage driver. But we found overlay also has a problem. But the problem actually are pretty easy to resolve by upgrading the kernel version to a newer one. For example, the pip install fails issue, which blocked our Python project for a while, but we found the kernel 4.5 actually resolved it perfectly. And also similarly, the overlay file system with the Unix daemon socket file, which is supported in kernel 4.7 and also backported to kernel 4.4. So now we are using the overlay storage driver, and we upgraded our kernel versions along the way several times to 4.8 now, which is pretty new. And also we upgraded Docker engine many times from 1.7 to 1.12.3 now. So to be honest, we didn't really test the device mapper, ZFS or BTRFS, some other storage drivers, but we think overlay works fast, and that's good. So a few tips. First one is the storage driver actually is very important for the stability of your Docker services. But you might hit problem. Fortunately, the Docker community is very, very hot. So you probably won't be the first one to hit the issue you hit. Somebody maybe already opened the issue on the GitHub, and somebody figured out a workaround, or the new version of kernel can perfectly resolve the issue. Actually, that's the case what we experienced. Every issue we hit has filed on GitHub, and we can easily find a solution. So it's not blocking as long as you can work around all of these issues. We will stick with overlay in Pinterest, and we heard overlay 2 will be the future default storage driver for Docker engine, but we found it's not as stable as overlay yet. I mentioned a little bit. We are running the kernel version 4.8 in-house. Yeah, we didn't find any problem when we upgrade the kernel version. Actually, I think it's amazing because the genius work has been done by Linux and a large community of the kernel development team. So the kernel upgrade actually is pretty low risk, and it can bring a lot of benefits to you. Not only the bug fix, but also some new features such as eBPF for providing performance issue or something, which is awesome. So we recommend you to use the newest kernel as much as possible. And we don't suggest to upgrade Docker engine in place because we found the Docker engine upgrading will kill your running containers on the host, which probably not acceptable. And also, it might change some default options for the engine. Then also you might not want it. So we bake the Docker engine into AMI, and we test new AMI on few dev instance for a while, then switch the AMI to the bigger scope. Then, to be honest, we use the Docker engine basically as an image to ship our binary. We are not using some fancy overlay network or some other advanced feature which Docker engine want to provide. We just use Docker engine as a minimalized way. And in that way, actually, we found the newer version of Docker engine is better because it fixed the issues and has a better support, better integration with the newer kernels. And another story I'd like to share is maybe special for Pinterest because Pinterest internally run many microservices, but for historical reason, we still keep maintaining 4 major monoliths repos. These are Python, Java, C++, Golang, and each repo has tons of dependencies. It's not a problem for production because, as Scott mentioned, the practice, you use a runtime image which could be very, very small to only have the binary and the runtime dependency. We use that way to build the runtime image. But for the build image, if you want to install all the dependency into a build image, it might take a long time. At the beginning, I created a build image for our Python repo, which has a lot of pip package dependency and also the Debian package dependency inside it. The image became 5 gigabytes. That's huge. And it takes 30 minutes to build. And because the mono repo, the dependency can't be changed by any developer randomly you don't know. It causes a lot of complaints because other developers has to rebuild the image, wait until 30 minutes. It's a huge waste. So we have to tackle this problem, special problem for the mono repo. I blame Python packaging tool a little bit because it doesn't have a good way to track the dependency like Maven or something. That's better. But anyway, we have to tackle this problem, and we used some trick. The principle is split the bigger image in one giant bigger image into smaller build image, and we move the next changed base image into a parent image for other child images, and we use makefile to manage the build order of them, and we use a special way to tag the image, use the checksum of the dependencies. So we have the script to calculate the checksum, and only the checksum change it will pull or build the image locally. In that way, we reduced the build time most of them into 3 minutes. So it's okay for developer now, and we are looking for another features which will be offered by Docker 1.13, which is an option called cache from. So it can look up some cache from remote place rather than the local host, which is awesome. I think probably we can average it by building some cache image in remote, and all the developers can benefit from it because it can pull from other place. And okay, that's an issue we hit with ECR at the beginning. So we were rate limited, which is unfortunate. And when we got rate limited, basically all the instances cannot do the Docker build or Docker push pull. So that's a several issue actually. But yeah, with the help of AWS support, we nailed out the cause, which is a shell script, which keep running the AWS ECR get logging in an infinite loop. So we stuck in there, and fortunately from the cloud tail, we can find out the source, identified the instance, and killed the shell script. Then we got it resolved. soon after it, we switched to cron script running on every host to execute this command and don't allow people to execute this get login command ad hocly. We also leverage environment variable called docker_config to make every host share one configuration file, which get configured by the cron script. So it works and prevent the issue happen again. But later I found another tool which is open sourced by AWS Labs, which is a great tool derived from the Docker credential helper. Basically, it provides binary artifacts to be invoked by Docker engine ad hocly whenever Docker engine needs to talk to a private registry. So yeah, the tool is written in Golang and build a very tiny binary. If you drop the tiny binary into the user bin folder and config the docker config.json file to use it, then it will work like a charm. It also has the token cached, so it won't invoke too many requests to the ECR. And one thing to notice is you have to put your own ECR URL into the config.json file. Otherwise, the Docker engine won't be able to find the parent image in ECR if you use Docker build command, which is a limitation of the Docker engine actually. But yeah, it's easy to work around. Next is a little bit experience with the Mesos integration. So before the Mesos version 1.0, it provided a URIs parameter you can specify in your marathon task definition. And in that parameter, you can point a tar file which have your Docker configuration credentials in it. Then in that way, Marathon and Mesos can talk to the private ECR very well. And since Mesos version 1.0, we have the docker-config options, which with that configured on each Mesos agent, you don't need to specify the URIs parameter for each task. Yeah, and another interesting thing I'd like to mention is the unified containerizer, which is Mesos community is actively working on. Basically, the Mesos unified containerizer can pull image from the ECR without Docker daemon. It's a bold move, but I'm pretty excited about that because you will only need one agent on the host, which is Mesos agent. You don't need to install Docker engine at all, but you can still benefit from the immutable artifacts from the Docker images. That's a good thing. And actually, I wish ECS agent probably can support such similar things in the future. Okay. Yeah, that's all. Maybe final comments. In Pinterest, obviously, our Docker role is just started. We haven't really worked on the orchestration, for example, the ECS integration or all kinds of scheduling issues or deploying multiple containers at once using pods. All these issues are interesting and we'd like to tackle, but yeah, that's next step for us. So finally, thanks for your attending, and I'm very happy here to share our story and obviously I already run out of the time, sorry. And so if you have questions, I'm happy to answer it off the stage. Thank you.